up-and-coming physics students. Today we'll take a step into the touring world of quantum theories.
Quantum mechanics is used to describe interactions between subatomic particles, how they can communicate infinitely fast, are in every possible state at once, and replace the rational rules of classical mechanics and relativity for chaos.
Yes, subatomic particles are indeed spooky, but quantum mechanics does its best to mathematically model these haphazard annoyances.
Let's go!
A wave function occurs when a wave function reduces to a single eigenstate. It predicted that a parent wave function collapsed when a superposition forms between the quantum system state and the environment state. Some people believe that collapse does not occur and that it is only an illusion caused by irreversible interactions with the complex environment. The physical origin of the wave function collapse, including the origin of the randomness of the collapse process. The existence of the collapse of the wave function seems natural, but the random discontinuous motion of particles might provide a random source to collapse the wave function, which might be the physical origin of the wave function's collapse. Although the collapse of the wave function just releases the randomness and discontinuity of motion, it might result in random discontinuous motion of particles. The measurement problem with the wave function collapse is whether it occurs or not and how. We are unable to observe the occurrence because it has risen a number of interpretations that will all need to be answered. As described by the linear exponential equation here, the quantum particle exists in all possible states, but when measured, it is only detected only in one of its states. It is suggested that when a wave function is measured by a microscopic device, it will not follow the linear exponential equation. It will instantly collapse into the wave function that corresponds to the definite measurement results. There are two ways to solve this measurement problem, and they are the de Broglie-Bohm theory and the many worlds interpretation. The de Broglie-Bohm theory takes a wave function as an incomplete description of it and adds hidden variables to explain the definite results. The many worlds interpretation explains the definite experience in one of the worlds from the many worlds and regards the wave function as a complete description of the whole world. You can reference the wave function and quantum reality by Sean Gao for more information on the de Broglie-Bohm theory and the many worlds interpretation.
So hi you guys, I'm Cassidy and I'll be talking about the quantum mechanics of the atomic theory, and a little subcategory is electron cloud. The atomic theory is it basically expanded on the law of conservation in mass and the definite proportions, that they came up with 5 premises. The first one being that elements in this purest state are particles that are called atoms, right? And then the second one is that the atoms that are basically the same are the same throughout. And then the third one is that to tell atoms apart is by their atomic weight. Okay, so the fourth one is that when atoms are added together and united together, they can make chemical compounds. And then the fifth one is that atoms can either be created or destroyed in a chemical reaction. They're just changed by its grouping. And then I'll talk about the evolution of the atomic models. The first one is the Dalton model in 1803, and he basically discovered that there was an atom. And he basically discovered that there's electrons. Rutherford's model was in 1911, and this is when he performed an experiment with gold foil, and he basically shot alpha particles through the gold foil, and he discovered that there's a nucleus. Wow. And then we have the Bohr model, and he proposed that electrons orbit in reflective orbit. And then we have our current model, which is basically that the masses and the electrons are everywhere. Like, everywhere. Like, you can't really pinpoint them. Something called superposition, which is explained by Emery. This is the electron cloud. The electron is everywhere and nowhere at the same time, which is really hard to think about because you can't play peekaboo and be 2 places at once, but electrons can. They mastered hide and seek. We can use the probability of density, which is the electron cloud is more dense in the center, and it's not necessarily a higher chance that the electron is there, but it's kind of like the electron is moving here more frequently. Now we're going to move on to the different positions that an electron cloud can take. This is the first one. This is the first S. An example of this is hydrogen. And then there's the second energy level, 2S. And it's a little bigger because it's more full. An example of this is helium, noble gas. And then we get into our 2P levels of our X, Y, and Z. Over here I drew a rough cardinal system of how it would look with the origin being in the middle. And this is basically where it would be kind of split in half, where the electrons would actually be. And then we'll go on to where I got my sources and where you can find your sources as well. The resonance structure is that basically in a compound, these bonds can change throughout and it's never stable. And it really interests me because of superposition. Superposition is like the electron is at two places at once. And the same reference right here because it's vibrating. You know, like it's constantly changing. And that's what really interests me in the resonance structures of chemistry. And on top of that, I'm interested in the quantum mechanics, but in pharmacy and how it could impact pharmacy. And I really want to see how the quantum mechanical computers can help better how you can view these compounds. And the sources that I used were YouTube with Ted Talks and Dominic Williams. You can also YouTube Dominic Williams. He really explained it like to the point. And then I use wire.com. You can also use it. It gets the job done and you get like more information. UBCTE.org also provides really useful information. Universitytoday.com as well. It's kind of really up-to-date. Recommend it.
So an analogy of this would be kind of like if you flip a coin. So let's say I'm in North America and I flip a coin, which is a quarter, and then my friend in Asia also flips a coin. So as long as both coins are the same type of coin, same physical properties, and like chemically the same, made of the same thing, this principle should hold true. I flip it, it's on the ground, but I don't look at it. And then my other friend flips a coin and he doesn't look at it. So right now, both coins are at a state of superposition where it's not either heads or tails, but a mixture of the both. So until I look at it, I don't know what it is. So let's say I look at it, right? And it's heads. That means the coin my friend flipped in Asia has to be tails, since it's part of the quantum entanglement principle. If you have one pair of particles, it'll be two particles, and these are the possibilities of each spin, right? So it can either be up and down and up, both are down, or both are up. However, quantum mechanics tell us that they can't be the same thing. So these possibilities are gone, and what's left is just four things, but two possibilities. So this whole thing has a 50%. And this holds true even if it's four particles, right? So if it was four particles and two pairs, the possibilities would be up and down up, both down, and then the same thing. But quantum mechanics still tell us that the pairs can't be the same. So these are out. And then we have 8 options, but 4 choices. So that would still be 50%. However many you use, the superposition probability is still the same. You have 50% of being up and down, or 50% of being down and up. This is confusing because how is it possible upon analysis of one particle, the other one is proven to have the opposite property without communication of the other? If they're light years apart, there's no way they can send a signal faster than the speed of light, because it breaks the universal speed limit determined by Einstein's theory of special relativity. Einstein called this phenomenon spooky action at a distance, and he suggested that the answer to this was hidden variables. So this theory suggests that particles have a predestined spin to it, and in quantum mechanics there are no randomness, and every particle has like a predetermined hidden variable to what it actually is. And this is interesting because if communication is the key of understanding the properties of each particle, then implementation of these ideas can be made so that communicating without speaking or texting is necessary. So it would be cool to know what your friend is saying without him actually having to say it, because signals from brains are transmitted faster than the speed of light. Further implementation of this research could be applied to new kinds of coding for governments. These messages wouldn't be able to be hacked, so it would be secure coded messages that travel faster than the speed of light. More research on this topic can be found in a book written by Margaret Rogers Mancubes, known as Einstein's Theory of Quantum Entanglement, which further explains Einstein's logic with coming up with his hidden variables theory. And also an article written by Ryszard Horodecki and his colleagues on aps.org on quantum entanglement.
One really interesting and frustratingly puzzling aspect of quantum mechanics is the double slit experiment. This experiment exposed the true particle wave-esque nature of photons and a multitude of other infinitesimal entities. In 1927, Davidson and Germer performed the first double slit experiment, and since then it's been replicated numerous times, verifying its results. Here's the experiment. Electrons are shot one at a time through a slit in the screen and form a line on the other side. This would be a perfectly reasonable result for a particle. Next, electrons are shot one at a time through two slits in a film. Here we'd expect two lines similar to that which we got in the first experiment. However, this was not the case. What we detected was a wave-like interference pattern. This would mean on the way through the slit, electrons interacted with each other, even though there were no other electrons for them to interact with. This baffled scientists. But what was even more perplexing was the next part of the trial. This time, the electron acted as a particle. Two lines and zero interference patterns were observed. This was groundbreaking, world-shattering result. And at the time, it seemed completely nonsensical. However, quantum mechanics can explain this result with one of the two leading interpretations, the Copenhagen interpretation and the many worlds interpretation. In the Copenhagen interpretation, the electron goes through one slit, the other slit, neither slits, and both slits, all at the same time as a wave of probability. This accounts for the interferences between electrons, which was observed in the second part of this experiment. The interpretation can also be used to explain the enigmatic results of the third experiment, with what's known as the observer effect. The observer effect reasons that the cause for the results changing when the particle was observed is due to the probabilistic properties of the natural world. By observing the electron, we force nature to roll the dice and give a concrete position of the electron, snapping it out of superposition and forcing it to act as a particle. The many worlds interpretation can also be used to explain these results, although I prefer the first explanation. In the many worlds interpretation, the universe splits into all possible outcomes every time an observation is made. If you would like to learn more about the many worlds interpretation, there is an article called Quantum Suicide by Jack Clark that does a great job explaining the implications caused by the many worlds interpretation. If you find this experiment interesting and would like to learn more about it or quantum physics, you should check out the book Quantum Physics: From Illusion to Reality by Sean Gao.
In quantum mechanics, the best we can do to calculate quantum particles is to calculate probability. We know that, just like everything else, quantum objects are both a wave and a particle. So we use the concept of Heisenberg's uncertainty principle to calculate them. The Heisenberg principle, or uncertainty principle, states that we cannot know the position and the momentum of a particle with absolute precision. We cannot measure the position or momentum of a particle with absolute precision. In short, it says that you cannot know the position and momentum of a particle at the same time. When measuring a quantum object or particle, you can only really know either the position or momentum. We know that a particle only exists in one point at any given time, and a wave is a disturbance with no set position. In quantum mechanics, the best we can do to calculate quantum particles is to calculate probability. We know that, just like everything else, quantum objects are both a wave and a particle, so we use the concept of Heisenberg's uncertainty principle to calculate them. The uncertainty principle states that we cannot measure the position and the momentum of a particle with absolute precision. In short, it says that you cannot know the momentum and position of a particle at the same time. So this is Heisenberg's uncertainty principle, where delta x is the uncertainty in position and delta y is the uncertainty in momentum. When measuring a quantum object or particle, again, you can only really know either the position or the momentum. We already know that a particle only exists in one point at any given time, represented by this box, and that a wave is a disturbance with no set position, so represented by this wave. The uncertainty principle is more like an idea to keep in mind when combining both a wave and a particle, since in order to find or calculate a quantum object, you need to use both the idea of a wave and a particle. So in this example, to reduce uncertainty in position, you must increase uncertainty in momentum. So let's say these two boxes represent position. If you want to know a more precise position, you would decrease your position, but in doing so, you would become less certain of the momentum. And let's say you wanted to know more about momentum. In that case, you would increase your range and position so that you would know more about the momentum. So your uncertainty in position would increase, but your uncertainty in momentum would decrease, which is again what this formula is saying. You cannot know both position and momentum at the same time. Keep in mind that your delta x and delta y will never be 0 because there will always be uncertainty. If delta x or delta y were 0, you would get 0, and then this principle will no longer be held true. If you would like to go more in depth about the concepts and the math and the controversy behind the uncertainty principle, you can check out this Stanford article, The Uncertainty Principle. Or if you're still confused about the relationship between momentum of position and momentum, you could check out this TED-Ed video called What is the Heisenberg Uncertainty Principle?